Thank you very much. Thank you all for coming to this talk. I'm Georgios Lillis. This talk refers to work that's a joint work with my colleagues, Kyriakos Katsigarakis and Georgios Giannakis and Dimitrios Rovas. Me and Kyriakos and Georgios are from Technical University of Crete, and Dimitrios is from UCL London. So this is a brief outline of the talk. I will start by describing the big picture of this work. So this work is a part of a big Horizon 2020 project. And then I will move on describing to you the transition between building information models and building energy performance simulation models. And then I will describe, so this transition is used in the platform I will talk about. And then I will move to describe to the description of the platform. I will talk about the concept of the platform, the architecture of the platform, the errors in the design, in the BIM files, and how these errors affect the results of the platform. And I will move to examples. And then I will close the talk with the achievements that we have, the features, the current features of the platform, the future features of the platform, and the conclusions. So here is the big picture. So this platform is a part of a Horizon, as I said, Horizon 2020 project called OPTEEMAL. The goal of the project is to do district retrofitting, and via implemented in 3 steps. The first step is the diagnosis of the district and the formulation of candidate retrofitting scenarios. The second step is the evaluation of the scenarios and the optimization operation. And the last step is the selection of the best scenario according to multiple criteria, and the exportation of this data to the stakeholders. So within this platform, the data of the buildings are in IFC step files, an IFC4 format, and then for the evaluation of the scenarios, we need a fast and reliable method that is going to take us from BIM, which is IFC4, to energy simulation programs such as Energy Plus, and where it uses building energy performance simulation models, which are IDF files. So to realize this transition, we need essentially to accomplish 2 steps, and we have to ensure 2 things. The first thing is that the geometric content of the IFC files are error-free, and I will talk about what is error-free. And the second requirement is that we need to have inside the IFC4 files the second-level space boundary topology of the buildings. So what is the second-level space boundaries? The second-level space boundaries are essentially the surfaces through which energy flows. And as you see on the right, there is a distinction between the architectural elements that you see on top and the space boundary topology, which are surfaces. So the architectural elements are solids, and the space boundary topology are a set of surfaces. So oftentimes, this set of surfaces, which are the second-level space boundary topology, is not contained inside IFC files, or is not correctly defined inside these files. Example here is exportation using Revit. On the left, you see the building model using Revit, and on the right, you see some exported first-level space boundaries, which are not defined correctly, as you see on the. So they are extended beyond the height of the room in the second floor. And of course, we tried also the exporter and the second level. These are the first level boundaries, and the second level boundaries are missing from the file. So in order to do this enhancement with the second level space boundaries, essentially we built a web-based platform that does this, which is illustrated in the figure below. So it has input an IFC file, an IFC4 file, which contains the geometric content of the architectural elements, and then enhances this file with a second level space boundary topology that you see on the right, and which includes various elements which refer to elements among the surface pairs. It can be either thermal if we have a construction, it can be an opening if we have an opening, it can be a virtual boundary if there's no construction or no opening, or it can be also a shading element. These shading elements are extruded architectural elements beyond the building envelope that shade the building of interest. So now I'm going to talk about the architecture of the platform. Basically, the platform is structured in three steps. The first step is that we extract the architectural elements, the geometric context of the architectural elements from IFC files. The second step, we implement an algorithm called CBIP, is a common boundary intersection projection algorithm that calculates the second level space boundary surfaces. In the last step, we enrich the input IFC files with these surfaces. So the platform is implemented, so all these steps are hosted on as Docker images on dedicated servers, and one image for every operation stage, and then multiple instances are activated in order to perform the service. So the user of the service interacts via a graphical user interface, a web-based graphical user interface, and asynchronous communication is established between the platform components based on enterprise service bus architecture. So for every IFC file the user uploads, there is a process tag, and a process is initiated, and the progress bar informs the user about the results of the process. So if after the user hits the run button, so the process starts, and if the bar becomes yellow, it means the process will end with an enriched IFC file, but some design errors exist, so the results might not be accurate. If it's green, the process will end with the enhanced IFC file with the topology and with the accurate results. And if it's red, it means that the imported IFC file, the uploaded IFC file is corrupted. So, and also we have an info button that informs the user regarding the quality of the IFC file and regarding the presence of errors. So, as I talk regarding errors, there are two kinds of errors that appear and affect the generation of the second level space boundary topology. The first error that appears also as user code 1001 is a space definition error. What happens in a space definition error? The space volume is not correctly defined in the IFC file. It's either smaller than the real space volume, and there is a gap between the space volume and the surrounding building construction, or it's larger than the surrounding building constructions, and in this case what happens is the space volume intersects with the surrounding building constructions. The second category of errors, which are site errors, and the platform appears with the error code 1002. Essentially, here either the site geometric representation is missing from the IFC file, or is not correct, and the site geometric representation intersects the building architectural geometric component. So in both cases, there is an error, and it comes from the fact that there is no site surface that is attached to the building, so there is no way to model the ground boundary conditions of our building energy performance simulation model. And also, in order to, we have also developed, I would like to add something to that, we have developed a model checking tool that is going to be in the future integrated to the platform, that informs not only the type of the error, also informs the user regarding where the error is and the surfaces that are not are related to this error. Either can be a space surfaces or site surfaces. So I will give you a brief demo of the operation of the platform. So, okay, so here we pick an IFC file, we open it, we upload it. And this speed depends on the connection, the internet connection. Then we hit the run button. Finished, and download the enhanced IFC. Open the solution. So we look for the space. We go. This is a nice example because we see various elements, either opaque or transparent, in the curtain wall. That is highlighted green color. We pick some spaces. Here are the space boundaries. As you can see, there are doors. There are solid plates. This is the aluminum plate that you see on the left. These are the transparent plates, the glazed, the roof. Here at the wall you have multiple spaces below, so you have multiple components, multiple space boundaries for the floor. These are external walls, and in the end you see the window, the internal walls. So, and then move more. So let me stop. Stop the video. It's so. No, just close. Yes. Yes. Okay. So, as I said, the platform is able to identify various kinds of space boundaries and also work in detail with curtain walls. And also, here is the example that you saw refers to a very simple building, but also we can work with more complex building geometries. Here is a building that is in one of the demo sites of the OPTEEMAL project. It's in a tower of 11 stories, and it has 3,798 space boundaries. As you see, this is some, didn't have space to put all of them here, but this is a complex geometry that appears in the ground floor. We have the slabs, as you see, all the which is also fragmented depending on the space topology, and the inner and the outside wall elements. So let me close the talk by talking about the achievements that we have so far. First of all, we support fully IFC4 files. Second, we support also the curtain wall elements and their embedded items such as doors, plates. You can understand we need this because these elements might play a different role in energy simulation. Some of them are operable, some of them are fixed, some of them might be opaque, some of them might be transparent. So we support not only curtain walls, we support curtain walls that are embedded inside other walls, but also curtain walls that are not embedded in walls that you see on the bottom. This is from the Turina tower. So, and also we support virtual space partitions, which are the areas that the two space volumes are attached without the physical boundary. And of course, the shading surfaces. These are the external surfaces that are parts of building slabs that are extruded, and they shade the building of interest. So let me talk about the features of the platform, the current features and the future features. First of all, if the IFC files are corrupted, then the platform terminates and the original IFC file cannot be enhanced, and this is declared with a red color shown. Now, if design errors exist, this affects the quality of the second level space boundary topology, and then these two bullets that you see highlight the need for having an IFC MPD check-in tool that is currently being under development and will be integrated in the future to the platform. So also we have a way tool that is also has been developed that performs the model checking, the error checking. It's an error checking tool that informs the user regarding the presence of design errors that affect the generation of the second level space boundary topology. And this tool will be integrated in the future in the platform, and then also we will generate a building energy performance simulation model at the end, which is going to be an idea of energy plus 5. So, and also in order to do that, we modified the Revit exporter in order to support material properties, curtain walls, and schedules of devices. So, to conclude, a web platform has been developed for enhancement of IFC files with the second level space boundary topology. The platform is based on 3 operational stages. First is the extraction of the necessary data from the IFC files. The second is the calculation of the second level space boundary topology. And the third is the enhancing of the IFC files with the surfaces of this topology. The platform has been demonstrated on simple and very complex geometries. And the contribution of the platform is twofold. First, it accelerates and helps the estimation of the building energy efficiency by automating the link between BIM and building energy performance simulation models. And the second supports the work in OPTEEMAL towards a realization of retrofitting, towards making optimal retrofitting decision support tool. Thank you very much. If you need access to the platform, please contact.